For today's lesson, we're doing optimization problems. Our objective here to solve applied maximum and minimum problems. You take a look at the picture here. You got this gargantuan box of cereal, but who really cares about the cereal? What we care about is the prize that's inside. And in this case, it's a Honda Civic. Okay, so the thing about, let's say, a lot of boxes that get manufactured, think of all those Apple products and how perfectly all those products fit within their boxes. Well, somebody had to design those things. And when they design them, they might have a certain uh, constraint. And let's say it's the volume. Maybe it's the volume of the cereal. They want to put a certain amount of cereal in the box. But whenever they're having to make thousands and thousands of these boxes, they want to cut down on the cost of the materials to make that box. So they want to minimize the surface area, which is basically the amount of cardboard they use to make that box. And so basically that is the idea behind an optimization problem. We want to find the smallest of something. We want to find the biggest of something, which is a major application, of course, of derivatives. So we're going to start this lesson by doing a little activity called the bigger box. We are employees of this guy, Lee J. Monroe, and we have been tasked with constructing a box that has maximum volume, but there's going to be some constraints on this box. Okay, so to make said box, we're going to take a sturdy piece of cardstock, which measures 8.5 by 11 inches, and we're going to cut a square from each one of these corners. It's going to make a net, as you can see over here in the corner here. And keeping in mind that this box has to be as voluminous as possible. It's got to have the largest volume. We got to maximize the volume for this box and then actually turn this thing into a box. Okay, so I'm going to start by looking at this little worksheet here, which is basically going to take us through the process of optimization. So each one of these things is one of the things that you got to consider whenever you're doing an optimization problem. The first one, after you read the problem, let's identify all the quantities that were given, sketch a little picture, and also make note of what it is that you have to maximize or minimize. What are you optimizing? All right, so we have ourselves a piece of paper, and of course we do have some pictures here that are given, and I'm basically going to duplicate those kind of pictures, but that's not always the case. All right, so I'm going to have a piece of paper, cardstock, right? And this is 8.5, 8.5 by 11 inches. And now we're going to take that thing. I'm going to center this so it looks a little bit better. Okay, that's better. And we're basically going to cut a square from each one of these corners. So it's going to go like this. These are fold lines, like so. However, we're going to take each one of these little corners and cut them away. And it's going to make a net for a box. And we're going to take that box, we're going to fold it up, and it's going to look sort of like this. There's one side of it, like this. All right, and looks like this should have been dotted, at least a part of it anyway. Okay, once again, I'm going to have to move this stuff around. Okay. All right, then. I've got myself a box that I'm going to make out of. Okay. All right, let's see. I've got pretty much all the quantities that were given. Oh, let's make note of this. We want max volume. All right, now I may have to come back to this phase if I don't have enough information in order to do the rest of it, but let's go ahead and move on to the next one. It says, write a primary equation for the quantity to be optimized. Primary equation is the equation that we're going to start with. Primary, of course, means first. We are maximizing volume, so I need an equation for volume. So ordinarily volume, this is a rectangular prism. It would be length times width times the height, right? And now notice that I've got essentially four variables here. You have the dependent variable of volume, and it depends on these three quantities here, the length times width times the height. which is sort of a problem. I want to whittle all of these down to just a single variable, just one of them. So you have an independent one and you have a dependent one. Otherwise, calculus gets a little bit messy. And that's where step number 3 comes in. Reduce the primary equation to one having a single independent variable using secondary equations. Okay, so I have a length, I have a width, and I have a height. I need to rewrite all of these things in terms of the same thing. So let's go back to our picture. Let's define a couple of things. Well, I have to take the same size square out of each one of these corners. I don't know how big that square is going to be, so why don't I just call it x? So here's an x here and here's an x there, right? And since all of these are the same, I'm going to have the same size square on each one of these corners. Joop, joop. Okay, now the first thing is, notice that whenever you cut this square off, this edge right here is going to join up with this edge. Here, let me zoom in just a little bit more. These two edges, I'm going to color code this for you. This edge is going to meet up with this edge. And when it does, it's going to form, let's say, this corner of the box. Or maybe it's actually that back corner. It doesn't matter. Maybe I just spun it around. And how big is that piece? It is x, because that's a square and all sides are the same, of course. So that's x, right? That's how high this box is. So in other words, what I just did is I found my first secondary equation. We've got our height is going to be equal to x. I guess we could have just put it in terms of h, but I didn't. I put it in terms of x. That's what I wanted to do. Okay, so now let's see if we can rewrite each of the other quantities, length and width, in terms of that x. And then I'm going to have one equation with just a single variable in it. Well, a single independent variable, I should say. All right, so let's see. Let's take this thing that I will call the length of the box. I'm going to call this the length. Boop. And it came from right here. Change the color again. It's this piece. Or the one that's over there on the left-hand side. Doesn't really matter. It's one of those. Okay, so how big is it? Well, it used to be 11. The whole thing used to be 11. But I took out this piece of the square and that piece of the square. I just basically took out two x's. It used to be 11. And now I subtracted out 2x. So that's how big the length is. 11 minus 2x. There we go. So here's our next secondary equation. We've got 11 minus 2x. And then finally our width, we'll say the width is this piece that's right there. And how big is it? So, of course, it's originally L. And then our length now comes from this piece of the diagram, or maybe this one down here. I'll use this one up here because it's not quite as crowded. Okay, so just like the length, I'm going to take the whole entire side of this piece of paper, which is 8.5, and I'm going to take away an x from each one of these sides. How big is it? 8.5 minus 2 x's. 8.5 minus 2x. So there's our secondary equations. We're going to use those to rewrite the equation for volume, which used to be length times width times height. Just take these things out and then substitute in all of these little quantities. And then I'm going to have a single independent variable. So the length is 11 minus 2x. Boop, boop. All right, and our width here is 8.5 minus 2x. And then finally, our height is x. There we go. That was the big goal for this third problem, this third thing. We drew a picture, marked quantities. We came up with a primary equation, whatever it is that we're going to optimize. In this case, we wanted max volume, so we came up with an equation for the volume. It had too many variables in it, so we had to get rid of some of those variables with some secondary equation. I had to go back to the drawing board and try to put the length, the width, and the height all in terms of a single variable. And I just happened to choose the x. Okay, so what I would like for you to do in preparation for the next video is to go ahead and expand this thing out. And the reason why you